This class discusses the multiplication rule and introduces the concept of independence. Recall the formula to calculate conditional probabilities. If A and B are events, probability of B given A equals probability A and B divided by probability of A. If we multiply probability of A on both sides of the equation, we get the general multiplication rule. It says that probability of A and B equals to probability of A times probability of B given A. This formula can be used to calculate probability A and B in some scenarios. For the 113th Congress, 18.7% of the members are senators, and 53% of the senators are Democrats. We define two events. Let D be the member selected being a Democrat. Let S be the member selected being a senator. The 18.7% is essentially probability of S. The 53% is essentially the probability of D given S, a conditional probability. It is easy to get confused. Why is one probability unconditional and one conditional? When we say 18.7% of the members are senators, this 18.7% means the proportion of senators out of all Congress members. However, when we say 53% of the senators are Democrats, we limit the members to senators. This 53% is the proportion of Democratic senators out of all senators. See, when we talk about 18.7% and 53%, we refer to different sample spaces. The sample space of the latter is just an event of the former. Therefore, this 53% is essentially a conditional probability, although there is no word given in the description. What is the probability that a randomly selected member of the 113th Congress is a Democratic senator? This question asks for the probability of S and D. Applying the formula we discussed in the previous slide, probability of S and D equals probability of S times probability of D given S, or 0.187 times 0.530 equals 0.099. This probability, so the probability that a randomly selected member of the 113th Congress is a Democratic senator is 0.099. Let's check a different example. A class has 40 students with 17 males and 23 females. Two students are selected at random from the class without replacement. Find the probability that the first student selected is female and the second is male. To solve this problem, we can define two events. Let F1 be the event that the first student is female. Let M2 be the event that the second student is male. This question asks for the probability of F1 and M2. Applying the formula we just discussed, probability of F1 and M2 equals to probability of F1 times probability of M2 given F1. For probability of F1, it is exactly the proportion of female students, or 23 over 40. For probability of M2 given F1, because a female is selected, there are only 17 male students and 22 female students left. Probability of M2 given F1 is exactly the proportion of males in the remaining students, which is 17 over 39. Do the math, we get 0.251, which is the probability that the first student selected is female and the second is male. The probability can also be demonstrated using a tree diagram. It lists all possible scenarios. The first student selected can be a female or a male, with probability 23 over 40. The first student selected is a female, with probability 17 over 40. The first student selected is a male. After one student is selected, there are 39 students left. If the first student selected is a female, there are 22 females and 17 males left. Then the conditional probability of the second student selected being a female is 22 over 39, and the conditional probability of the second student selected being a male is 17 over 39. Similarly, you can get the remaining scenarios when the first student selected is a male. This tree diagram is helpful if you are confused about how to calculate probability in such problem. We will formally define independence. Event B is said to be independent of event A if probability of B given A equals a probability of B. It means that the probability of B remains the same even if we know that event A occurs. In another word, no matter whether event A occurs or not, the probability of event B is the same. Let's consider the experiment of selecting one card from a deck of 52 cards. Let event K be a king and event F be a face card. Event K and F are not independent. Heuristically, they should not be independent because king is one of the face card. Let us check it by the definition. Probability of K given F is 4 over 12 because there are 4 kings and 12 face cards in a deck. Probability of K is 4 over 52 because a deck has 52 cards. Clearly, probability of K given F is not equal to probability of K. By definition, K and F are not independent. Now let H be the event that a heart is selected. Probability of K given H equals 1 over 13 because there are 13 hearts and only exactly one king of hearts. Probability of K is 4 over 52 or 1 over 13. Probability of K given H equals probability of K. By definition, K and H are independent. If we know that A and B are independent, the multiplication rule can be simplified. Now, probability of A and B equals probability of A times probability of B. Conversely, if probability A and B equals probability A times probability of B, we can say that A and B are independent. This rule can be further extended. If A, B, C are independent, then probability A and B and C equals the product of probability of A, probability of B, probability of C. An American roulette wheel contains 38 numbers, of which 18 are red, 18 are black, and 2 are green. When the roulette wheel is spun, the ball is equally likely to land on any of the 38 numbers. In 3 plays at a roulette wheel, what is the probability that the ball will land on green the first time and on black the second and the third times? This probability involves 3 events. G1 means that the ball lands on green the first time. B2 means that the ball lands on black the second time. B3 means that the ball lands on black on the third time. The question asks for the probability of G1 and B2 and B3. Here we claim that these 3 events are independent because the result of each play is completely random and does not depend on the result of the previous play. Applying the special multiplication rule, because these 3 events are independent, probability of G1 and B2 and B3 equals the product of probability of G1, probability of B2, and the probability of B3. Each of these probabilities can be easily calculated. It is exactly the proportion of each color. For green, probability of G1 is 2 over 38 because we have 2 green. For both probability B2 and probability B3, the probability is 18 over 38 because there are 18 blacks. The probability that the ball will land on green the first time and on black the second time and the third time is 0.012. We want to emphasize that mutually exclusive and independent are 2 different concepts. Mutually exclusive events are those that cannot occur simultaneously. Independent events are those for which the occurrence of one does not affect the probability of the other occurring. Assume that A and B are mutually exclusive. If A happens, B cannot happen. It means that the occurrence of A affects the probability of B. Therefore, A and B are not independent. A more rigorous statement is that 2 or more non-impossible events cannot be both mutually exclusive and independent. If A and B are mutually exclusive, A and B is an empty set and hence probability of A and B equals 0. If A and B are independent, then probability of A and B equals probability of A times probability of B. Connect these 2 equations. We get probability of A times probability of B equals 0, which implies that probability of A equals 0 or probability of B equals 0, or at least one of A or B is impossible. Let's repeat the conclusion. 2 or more non-impossible events cannot be both mutually exclusive and independent.